Hi guys, welcome to my YouTube channel. So in today's video, I'm going to talk about the Wilson's theorem. The Wilson's theorem states that if n is a prime number and it's also greater than 1, then n minus 1 factorial is congruent to negative 1 in mod n. And there's also a theorem called the Slope's theorem that states that n minus 2 factorial is congruent to 1 in mod n, which we will prove in one of our examples. In the first example, we have 12 factorial. And since the Wilson's theorem states that n minus 1 factorial is congruent to negative 1 in mod n, and 13 is a prime number, and 12 is 13 minus 1 equals 12. So then we know that 12 factorial must be negative 1 in mod 13. And that's our answer. Moving on to example 2. So we know that 4 factorial must be congruent to negative 1 in mod 5. But the problem is asking us to find 3 factorial. So what we could do is to rewrite this 4 factorial as 4 times 3 factorial is congruent to negative 1 mod 5. And now we have to get rid of this 4 to find what 3 factorial is. So in this case, we could use the Euclidean algorithm to find the modular inverse of 4 in mod 5 so that we can get rid of this 4 in the front. So if you don't know what Euclidean algorithm is, you can check out one of my previous videos. Is in my channel, and I hope it will be helpful. So now first, let's rewrite this equation. So what we could do is first let's put 5 here, and it's equal to 4 times 1 plus 1. And then we move the 4, oh wait, we can stop here since we end up with 1. And now let's rewrite this as 1 is equal to 5 subtract 4 times 1. Now we know that the format of this equation is actually am plus bn is equal to 1. So let's put the negative 1 inside a bracket. So let's write this as 1 times 5 plus negative 1 times 4 is equal to 1. So the number that's in front of 4 would be the modular inverse that we need to find. So in this case, now we can just multiply by negative 1 on both sides, and we will have 3 factorial is congruent to 1 mod 5, which proves or previous, I talked about the Slope's theorem. This is what it's look like, and since 3 is 5 subtract 2, and we know that the Slope's theorem is valid in this case. Example 3, we have 89 factorial is congruent to what number in mod 61? The numbers are a lot bigger, but don't be intimidated by this problem. So based on the Wilson's theorem, we know that 60 factorial is congruent to negative 1 in mod 61. So if we rewrite this to see the 60 factorial more clearly, we would have 89 times 88 times 87 times 86 times 85 all the way to 61 times 60 factorial is congruent to what number in mod 61. So basically we can just cross this part because we know it's congruent to negative 1 in mod 61. So this will become negative 1. But the problem is there's still so many numbers in front of the negative 1. So how do we solve this problem? The key is to notice that there's a 61 inside of the 89 factorial. So 61 is basically congruent to 0 in mod 61, right? Because when you divide 61 by 61, it gives you 1. There is no remainder. So basically, the remainder is 0 in this case, so then that's why it's congruent to 0 in mod 61. So everything in front of it multiplied by 0 is just going to be 0. So the answer to this problem will just be 0 mod 61. Moving on to example 4. So now we have 97 factorial is congruent to what number in mod 101. So first we know that 100 factorial is congruent to -1 mod 101. And let's try to break this apart to find 97 factorial, to see 97 factorial more clearly. So we can rewrite this as 100 times 99 times 98 times 97 factorial is congruent to -1 mod 101. And now 100 in mod 101 is basically just -1, because we know that 100 subtracted by 101 is -1. So that is actually congruent to 100 in mod 101. So this is -1. So this is -2, -3 times 97 factorial is congruent to -1 mod 101. And now if we multiply these three terms together, we have -6 times 97 factorial and then -1 mod 101. So let's divide it by -1 because I don't like the negative in front of the 6. So we have 6 times 97 factorial is congruent to 1 mod 101. And now let's use the Euclidean algorithm to find the inverse of 6 in mod 101. So we have 101 is equal to 6 times 16 plus 5, and then we have 6 is equal to, drop the 5 down, so we have 5 times 1 plus 1. So since we have a remainder of 1 here, we can stop and let's rewrite this as 1 is equal to 6, subtract 1 times 5. And then let's do some substitution. So we have to rewrite this as well. So it's 5 equals to 101, subtract 6 times 16. So let's substitute this part, which is 5, into this. So now we have 1 equals to 6, subtract 101, subtract 6 times 16. And then if we distribute the negatives, the -1 in the front, we have 1 equals to 6, subtract 1 times 101 plus 6 times 16. And then we have 7 times 16, subtract 1 times 101. So the number in front of it, the 6, it should be 17 times 6. Yep. So the number in front of it is 17, so we just multiply by 17, and this is become a 1, and then we have 97 factorial is congruent to 17 mod 101, and that's our answer. Now we are moving on to example 5. So I want you guys to try this on your own first, and we'll come back in a minute. So this one is definitely more complicated than our previous examples. Based on the Wilson's theorem, we know that 60 factorial is congruent to -1 mod 61. And if we break this apart, to see the 53 factorial more clearly, we would have 60 times 59 times 58 times 57 times 56 all the way to 53 prime is congruent to -1 mod 61. So 60 in mod 61 is basically -1, and there will be -2, -3, -4, -5, -6, yes, -7, and then 53 factorial. So if we multiply this whole thing together, we will get -mod 5040 times 53 factorial is equal to -1 mod 61. So similarly, I would just divide it by -1 on both sides, and I'll have 5040 times 53 prime is congruent to 1 mod 61. And now let's try to simplify this number further so we can find the inverse of this part easier. So let's divide it by this 61 to find the remainder first. So we have 8, and then goes there. $38. So we have the number 38. So now let's cross this out, and we have 38. Now let's try to use the Euclidean algorithm again to find the inverse of 38, so then we can isolate the 53 factorial out. So let's place the 61 here is equal to 38 times 1 plus 23. 38 equals to 23 times 1 plus 15, and then bring 23 down, and then 15 times 8 times 1 plus 7, 8 equals to 7 times 1 plus 1, yep. And then now let's rewrite all of these expressions. So 1 equals to 7, and then goes to 15, subtract 8 times 1, and then 8 is equal to 23, subtract 15 times 1, 15 is equal to 38, subtract 23 times 1, and 23 is equal to 61, subtract 38 times 1. And now basically what you have to do is try to substitute these values into these numbers. So, and then eventually you would get to 1 is equal to something times 61 plus n times 38. Since this is a very long substitution process, I'm not going to show in this video, but it will be in my PDF file down below. And after all of these substitution, you will get 1 is equal to 5 times 61, subtract 8 times 38. Now we know that -8 will be the modular inverse of 38 in mod 101. And now let's go back to the problem. So what we have to do now is to multiply both sides by -8. And we can cross this apart out, so we would have 53 factorial is equal to -8 mod 61. So if you want a positive solution, just simply add 61 to this side, and we would have 53 mod 61. And that will be your final answer.